Hey everyone, welcome back to the channel Code with AKJ. Today is day 36 of solving Geeks for Geeks problem of the day. Today's question is facing the sun. It's asked in Amazon. So the question says here, given an array height representing the heights of building, you have to count the buildings that will see the sunrise. Here we are assuming that the sunrise is just on the side of the array, starting point, which would be on the left side of these buildings. So the height of the building should be strictly greater than the height of the buildings left in order to see the sun. So here in this given diagram, we can clearly say that the building 1, 3 and 5 can see the sunrise. So here the answer would be 3, as 7 is the first element, it can see the sunrise. 4 can't see the sunrise as 7 is hiding it, and 8 can see, 2 can't see the sunrise, and 9 also can see the sunrise. So in this case, the output would be 3, as 3 buildings can see the sunrise. So coming to the second example, the first building can see the sunrise, and coming to the remaining buildings, their heights are greater than the buildings to its left. So all buildings can see the sunrise. So in this case, our answer would be 4, as the buildings' heights are in ascending order. So let's analyze this example and we'll come up with a brute force solution. So here's the first example, and since the first building can see the sunrise, we'll count it as, since the second building height is smaller than the first building hides the sunrise from it, so the second building can't see the sunrise. Coming to the third building, its height is greater than the heights of the previous buildings to its left, so it can view the sunrise. Coming to the fourth, the third building hides it from the sunrise, so fourth building can't see the sunrise. And coming to the last building, its height is greater than all the remaining buildings, so it can easily see the sunrise. So in this case, the answer would be 3. So the brute force approach here would be to check for each building the neighbors to its left, and we'll compare the height with the current building, and if it is the highest, then it can view the sunrise, and if it is not, it cannot view the sunrise. So here we'll use two for loops. So for each building, we'll check all the buildings to its left and we'll compare the heights. And if the height of the current element is the tallest among all the buildings to its left, we'll mark can see rise as true. And finally, after taking all these for loops, if the variable can see sunrise becomes true, then we can count the building as a valid building which can see the sunrise, and if not, we'll move on to the next building. So in this way, with the help of two for loops, we can find the number of buildings which can see the sunrise. So here the time complexity would be O of n square and space complexity would be O of 1. So let's move on to the code. So here's the code for the brute force approach. Initially I have taken the count value, which is 0, and we'll run over this buildings vector. So initially I have taken the can see sunrise variable, and initially it would be true. So and we'll take another for loop to check all the buildings to its left. So it runs from 0 to I, and we'll compare the current height with all the buildings to its left. So if in any case the height of the previous building is greater than to the current building's height, then we'll mark as false and we'll break it from the loop. And finally we'll check if can see is true or false. If it is true, we'll increment the count, and if it not, we'll compare the next building. So in this way, we'll calculate the count of the buildings which can see the sunrise, and we'll finally return that count variable. So let's compile and run. So let's submit. As you can see, this problem got accepted successfully, but here the time complexity would be O of n square and space complexity would be O of 1, but it is not as our expected time complexity. So we'll try to optimize this approach and we'll complete this problem in our expected time complexity and auxiliary space. So now let's move on to the optimal approach, which is much more efficient. So in the optimal solution, instead of checking each building's left side, we'll keep track of the tallest building we have encountered so far. So if the current building height is greater than this maximum height, it can see the sunrise, and we'll update the maximum height as we go around this heights vector. So let's try run this approach with this example. We have taken a max so far variable which would be initially 0. We'll iterate over this array and we'll compare this particular height with the max so far building, and if it is greater we'll update the max so far building height and we'll increment the count as it can view the sunrise. So initially it would be 0, so the first element always can see the sunrise view. So we'll increment the count value to 1 and we'll update the max so far building which would be the height of the current first element. And we'll move on to the second building and we'll compare the height of the second building with the max so far height building. And since it is false, it means the second building can't view the sunrise, and since the first building is hiding it to view the sunrise. And coming to the third building, we'll compare the height of the third building with the max so far height building. Since it is true, we'll update the max so far height, which would be 8, and we'll increment the count as it can view the sunrise. Coming to the fourth building and third index, we'll compare the height. Since it is not greater than, so we'll return false from there, and we'll move on to the last building. Since the height of the last building is greater than the max so far value, we'll return true, and we'll update the max so far height and we'll increment the count. So since we have iterated over all the array, we'll after finishing this iteration, we'll return the count value, and in this case the count value would be 3. So in this way, we have optimized our approach and reduced our time complexity from O of n square to O of n. And since we didn't use any external data structure, our space complexity would be O of 1 as our expected time complexity and space complexity. So let's move on to the code and let's submit. So this is a code for the optimal approach we have discussed and try run using this first example. So here I've taken the count variable max so far and iterated over this height array, and I've compared the height with the max so far building value, and since if it is greater than the max so far height value, we'll increment the count and we'll update the variable max so far. And after finishing our iteration over the heights array, we'll return the count from it. So let's compile and run. So let's submit. As you can see, this problem also got accepted successfully. So here our time complexity and space complexity is matching with our expected time complexity and space complexity. So in today's video, we have discussed the approaches to solve the facing the sun problem. The brute force solution had a time complexity of O of n square, while the optimal solution improved that to O of n. So it's a great reminder of how important it is to optimize solutions, especially when working with larger inputs. So if you found this video helpful, please give it a thumbs up and subscribe for more daily coding solutions. And let me know in the comments if you'd like to cover any specific problems. So thanks for watching, and I'll see you later in the next video.